Welcome to the channel. This is Diploma 3 guy. Hope you'll enjoy the channel. Subscribe for more videos and hit the notification bell for more videos that I release. And today we're going to discuss about steam turbines. Steam turbines are also involved in thermodynamics, and this we are going to talk broadly about steam turbines, then solve some questions involved in steam turbines. Let's start. Gas turbines are literally made of two triangles, implying triangle 1 steam from the nozzle and triangle 2 steam entering the blade. These are combined to form a turbine shown below. And this we are going to discuss terms used in steam turbine. For example, I've drawn an example of a steam turbine. There we have some terms used in defining steam turbines. I'll quickly move to terms used in defining steam turbines. 1. It's the CI. This is the velocity of the steam at the inlet. Alpha I, angle of the steam at the blade velocity. CRI, relative velocity at the inlet. BI, relative velocity angle at the inlet. CB, blade velocity. CFI and CFE, this is the axial velocity to the blade subjected to the steam at the inlet and outlet respectively. CAE, absolute velocity at the exit by combining both CRE plus CB. CW is the driving force, and the rate of change of the driving force is called CW. I hope you will memorize this diagram before we move to the next topic, and you have to really memorize the terms used for you to be able to solve other questions involved in the steam turbine. Important notes to take. Trigonometry is used in solving steam turbine problem. If the blades are symmetrical, that means BI, velocity of the steam at the inlet, and the velocity of the steam at the outlet, that means it's symmetrical. If the steam does not experience friction, then CRE is equals to CRI. If the velocity of the steam is reduced by friction, then CRE over CRI is equals to K, where K is the blade velocity coefficient. These are some of the important notes to take. Formula for diagram efficiency. Diagram efficiency is equals to rate of doing work per unit mass of steam over energy supplied per unit mass of steam. Take note that is per unit mass of steam. And formula is gotten by mass times CB over rate of change of driving force. CB is equals to blade velocity over mass C squared over 2. But change of the driving force is equals to 2CAI cos alpha I minus CB. But CRI cos BI is equals to CAI cos alpha I minus CB. Then rate of change of driving force is equals to 2CRI cos BI. Then we quickly insert the value of CRI cos BI, which is CAI cos alpha I minus CB. So diagram efficiency is equals to 2 over 2 CB blade velocity 2 into brackets cos I cos AI over CAI cos I alpha I minus CB over CAI squared. That means 4CB over CAI. If you solve the equation, you get that the rate of diagram efficiency is equals to 4CB over CAI is equals into bracket CAI cos alpha I minus CB. In our question papers, you'll find that the teachers might ask you to prove that diagram efficiency is equals to 4CB over CAI into bracket CAI cos alpha I minus CB over CAI. You're supposed to get this correct. Note that CB over CAI is equals to blade speed ratio. I hope you'll understand that. We're going to work on velocity compounding steam turbines. This involves two velocity two. It involves a steam turbine with two row. That means in your later exams, you're expected to do a question that has two row velocity impulse turbine, but you're also expected to solve questions involving this. I'll further move directly into the question so that you might know how to solve this question. So that, and the question reads: the first stage turbine is a two-row velocity impulse. The steam velocity is 600 meters per second. The mean blade velocity is 120 meters per second, and the blade velocity coefficient is 0.9. The nozzle angle is 16 degrees, and the exit angle of the first row of the moving blade fixed, and the second row is 18, 21, and 35 degrees respectively. Calculate blade inlet angles in each row, driving force at each row, and the axial thrust on the wheel with a mass flow rate of 1 kg meters per second. The diagram power per kgs per second, and the diagram efficiency of the wheel. Maximum possible diagram efficiency. Important to write this so that you might not confuse. That means that CAI, the speed of the steam entering the turbine, is 600 meters per second. Blade velocity is 120 meters per second. The coefficient of friction is 0.9. Alpha I 16 degrees. Exit angles is 18, 21, and 35. Take that the angles are named in order without interchanging. In drawing the turbines, the second row is usually smaller than the first row turbine as shown above. Now we'll have to apply trigonometry to get all the values of the terms used as indicated before in the tutorial. I've already drawn the steam turbines, the first row and the second row of the steam turbine. You have to memorize and study the terms used before you are able to solve this question. I've equally, as you can see in both drawings, the blade velocity is equal in all steam turbines of the first row and the second row. Now we'll quickly solve the first row equations. In the first row equations, we're going to start by getting the axial velocity at the inlet of the first row. That is 600 sin 16, which is 165.4 meters per second. To get the change of driving force in the first row, we get it 456.76. To get the blade angle of the first row, the blade angle of the first row is 19 degrees. We use tan. Take CRI, get is 485.79 meters per second. CRI, here is the trap. We say that K is the coefficient of friction, so it is 0.9 times 485.79. You get that it's 437.26. Change axial velocity at the outlet. Then we use also trigonometry and we get it's 135.1 meters per second. CWR, changing thrust velocity at the exit. You get that it's 295. Blade angle at the exit, we use tan to get it. CAI is equals to 325.19 meters per second. That's the first row. That's the equation of the first row. I'll then move to the equation of the second row. CAI in the second stage is, we take the coefficient of friction from the first stage to get the CAI of the second stage. That is 0.9 times 325.19 meters per second. You get that it's 292.7 meters per second. CFI2, CFI, CW2, get all the figures, and I'll quickly move on to dealing with the question. We are asked that the total driving force of both the first stage and the second stage. The total driving force is the change of the driving force. We combine them and we are told that the mass flow rate is 1, and to get the driving force is mass flow rate times change in the driving force. That is 872 plus 289. We get it 1162.52 newtons. Power output is equals to driving force times blade velocity. Driving force was 1162.52 newtons times 120 meters per second. We are supposed to change that into SI units. That's why we are multiplying times 10 raised to negative 3. We get that that's around 140 kilowatts per kg per second. Energy supplied, we say that energy supplied is mass flow rate times the velocity of the steam entering the blade divided by 2. That is 1 times 600 squared over 2. Take note that we are also changing into SI unit. That's why we are multiplying 2 times 10 raised power 3. You get that is 180 kilowatts. Diagram efficiency. We say that diagram efficiency is equals to power output over energy supplied to the wheel, and we found that power output was 140 kilowatts times 10 raised power 3 times 2 over 600 squared. You get that the diagram efficiency is 77.9%. Max efficiency is gotten by cos squared alpha I, and alpha is 16. So you get that maximum velocity of the steam is 92.4 degrees. I hope you've learned a lot from the video. This will help you to do this question. Usually you are given a harder question like this for 20 marks, so that this the most vital example that I give you. Feel free to hit me at my social media account for more information. Next time we are going to deal with fluid mechanics about dimensional analysis. Hope you'll get something from this, and Consider subscribing to the channel. And hit the notification bell. Thank you. Support the video. Share it with your friends, your colleagues in your classroom,